the main. So when a model also of new techniques come, they also give us new insight. So the heliosysmology, when it started, it gives us like many unknown stuff which the theoretical people could not imagine to find. So this is one of the things I'll just summarize, that what heliosysmology gives us about the sun. Then we eventually go to the theoretical model, that how we'll do with this. Again, it's not going. Yes. So here I'm just giving you that what I have said just in the first lecture. So what heliosysmology finds? So first is the solar structure, and that is also consistent with our standard solar model. Core, then the radiative zone, the radiation is happening, then the tachocline region, and then from there the convection, and then you're seeing the photosphere. Then from photosphere you have chromosphere, and that Krishna will do next day. So you'll see the corona and everything. So heliosysmology gives us this thing. So radiative interior, outer 1/3 is convective. So that is also we get from this. So 30% of the outer solar convection zone is a convective. Whether there is a home to dynamo. So what is dynamo? Probably you know already, the dynamo is just changing the, when you're like power off, it's just mechanical energy to electrical energy. Here it is the kinetic energy which is coming from the convection. The dynamo make it to magnetic energy. So the dynamo is happening in this convection zone, which is the source of everything. Because without magnetic field, as I said, nothing will happen. So this is the dynamo. So I will go through it, that how dynamo and everything comes. And this is another good thing about the heliosysmology, is the sun doesn't rotate solid, like in solid body way. The sun has a differential rotation. So that is heliosysmology finding very quantitatively. And it is rotating faster, so the error and everything was smaller in this. So we are like more certain about it. So here I show how the heliosysmology profile gives us about the differential rotation. So rotation differentially, and you see equator is rotating faster than the pole. So equator is rotating 24 days, and pole is rotating 30 days. So this gives the differential rotation. Now again, if some of you have done any fluid mechanics course, and then you'll see that when you are doing some of the, how do I say, if you're heating water, then you need to keep on heating it. So if it crosses some Rayleigh number, I do not know whether some certain condition, the temperature gradient, then only it becomes convective. And then if it is a magnetic field, then it interacts with it. So it's a like whole of very different things are going on there. So in this convection zone, this differential rotation plays like very important role in generating this kind of magnetic field. Because just imagine, this is rotating faster and this is rotating, so there will be shear, right? So suppose you are rotating something, this is I'm rotating, this is rotating faster, this is rotating not faster, so there will be distortion, there will be some shear. So the differential rotation will help in this way. So this is main finding from the heliosysmology. Now we go a little bit more deeper. So if you see, heliosysmology found a flow called meridional flow. So this is also to relate you with the Earth. So if you see in Earth atmosphere, we have some kind of cell called a meridional cell, or also you see in the sea, like we have this, all the Pacific Sea, Atlantic Sea, they have a Gulf Stream or something, they have a specific flow. So why it is happening, these are called the meridional flow. So if you have a sphere in an Earth theta cut, if you take, there is a large scale flow. So in the heliosysmology also find it in the solar interior. So if you see the photosphere and you just measure them, then you see from the equator to pole, there is a large scale flow going on. And then this flow also goes in and coming back to the equator, because for the mass conservation, mass goes to the pole, it should come back. But this downflow, here you see this downflow, the upflow is very easy because it's like observable from the heliosysmology, but the down in the density and everything changes, so uncertainty becomes very strong. So this result was quite debatable. So from 2010 and everything, some people say this doesn't exist. Some people say it is coming from the middle of the convection zone. So this paper came in Science in 2020 during Corona time, and they indeed found that the sun has a big one-cell circle. So the plasma flow goes from equator to pole and again coming back. So you will see how important is this for the dynamo perspective. So I'll also. So this is kind of the heliosysmology's finding. It's like just like getting stuck. Oh, okay. So now I start with giving you the magnetic field features. So these are all the heliosysmology. So when you see the sunspot and everything, so that started from 1600. So with the discovery of the telescope, the Galileo first found this the sunspot region. So from that, it's just always make curious to the human mind. So after 1600, 1700, people start on like looking them. So we have now 400 years of whole sunspot distribution. And if you see that when around 1600, there is also discovery that the William Gilbert found that the Earth is a big magnet. So that is also kind of discovery. After that, for the sun, it takes 300 years. In 1908 only, we found that the sunspots are like the very strong region of the magnetic field. And that is the first detection of the magnetic field outside of our Earth. So and then found that in many astrophysical body, they have also magnetic field. So that is the first discovery in 1908. And just imagine that after that discovery, people started to understand that why sun is generating magnetic field. And they found that magnetic field is associated with the most of the phenomena on the sun. So then there are, the successful model, I would say, is formulated by Eugene Parker in 1955. But before that, many people started to develop the magnetic model for the Earth. You know, the Earth is also a huge magnet. It has a magnetosphere. So then the 1955 Parker first formulated this. So I'll come to this model, that how our sun is just calculating this magnetic field and it has a cycle and every stuff. So probably all of you have seen this diagram. So this is the first one, is called the butterfly diagram. So suppose you have sunspot. I saw the Galileo photo, that is maybe in one instant. So suppose you take this and draw a time series. So every day, suppose you are observing. So we have the Kodaikanal, we have a lot of data from there and we have digitized them. So you see these data also showed this kind of, we have like consistent measurement from Kodaikanal, but by combining all other observatory, you'll find this kind of diagram that it's indeed follow a butterfly diagram. You see, it looks like butterfly. But one thing also you see, there is no sunspot above 30 or 40 degree, both of the hemisphere. So why is so? This is still an active field of research. We do not know that why the sunspot never appears at 60, 70 degree. They always appear below 45 degree. So in the beginning of the cycle, sunspot appears there and it starts to go towards equator. That's why it's called equatorward migration. And that is very important phenomena because it is not random. If you see from 400 years, sun is doing periodically again and again and again and again. So there must be a deterministic system which is going inside and creating this kind of phenomena. And also this is like the time latitude diagram. In time and latitude, you plot all of them. In the down, we are plotting the number with the time for all cycle. And you see the cyclic behavior. So this is the solar magnetic cycle. And any phenomena, you see the flare frequency, CME frequency, all correlates with the solar cycle. So if the sun is very active, it has like a lot of sunspot, it will be more active and it will give more CMEs. And the space weather event will be more active in that era. If sun is quiet, then we do not have more CME flares. So that's why studying the solar magnetic cycle is very important, that why sun is doing that. The why sun is creating this kind of sunspot structure, why it is bipolar. So many questions, that comes to us. And studying them, actually you are studying at the same time the fundamental physics and also how you are going to relate with the space weather. Now on the technology based era, we need to understand the space weather. And suppose if you can predict that whether how the next cycle will look like, if it is stronger or weaker, you can predict how the space weather event will look like. So that's why studying them is very important. Sorry, it goes a long way. Yes. So then the question is where these all things are coming, all the magnetic field. So which is like giving this support. So there I show you a closer look of the sunspot, just for your informative thing, that how the sunspot and everything look like. So sunspot, as you see, appear to be darker in visible wavelength. So the temperature is like, if you see anything, this is the 4500, 5800. So it always looks darker. And the reason the darker is like they have not enough energy. So when you see in the visible length, it just goes down. So the sunspots, if you see the side, they are also the granulation, the small turbulence like the convective scale. So this big structure always gives this idea that this is coming not only from the surface, rather it has a root down. If it is only the surface, then you see this kind of structure. So that's why it was argued that the sunspots are rooted deep interior. And then the idea put forward that the big rigorous convection is happening inside the star, inside the sun, and near the sunspot region, the energy should be going out. That's why you are seeing everything. But the sunspot region, energy cannot come out. So then it was fine from the plasma theory perspective that if you are like doing any convection or anything, then in presence of magnetic field, the energy transfer actually suppresses. So convection suppresses the energy transport. So that's why these are the strong magnetic region which is suppressing the energy transfer, and they are appearing as a black. And I will give you also like the very qualitative or like our present understanding how the sunspot forms. And this is also called the Hale law. So if you see the 1919, George Hilary Hale first found that he argued that the sunspot always appear bipolar. So it's a positive and negative always come side by side. And this is called Hale law. So if you see like the northern hemisphere positive negative, southern hemisphere will be negative positive, but they will come always same time. And another thing I want to mention, when you have this big flux loop, you see the material can also be trapped. Because magnetic field has the magnetic pressure associated with it. So when it erupts, it can put some of the plasma ring. So material can be trapped inside it too. So this is a closure loop. So if you want to understand how the CME and everything happening, we have to understand how the sunspot forms. So nowadays, people are also doing a realistic simulation of sunspot. And if you want to understand the space weather event for a long term, then you have to understand the cyclic behavior, how the sunspot are going with the time. So I will give you first how the sun is creating the sunspot cycle and the dynamo theory. Then I will briefly show the present effort that how they also calculate the sunspot. You cannot understand that, you cannot differentiate the realistic sunspot simulation and the observed. So nowadays is going, the computational methods are going in a very, very prospective way, I would say. Yeah, go ahead. Yeah. Ooh. This one. Uh-huh.
There are sunspot there is one not only the temperature difference, the magnetic field also changing for umbra and penumbra.
Right. Oh, so that is also, if you do the full scale simulation, how the energy transport is happening. Of course, that is true.
Someone once asked me a question about the sunspots. You said that the energy flow is being suppressed due to magnetic field. So the guy asked me, where is the energy?
Oh, no. So if you see like the whole global energy scale, that is dissipation, it's like channelized to other thing. So suppose it's a big spherical cell. So where the magnetic region is there, probably energy is not transporting there, but energy is getting suppressed to side. Yeah. So turbulence, of course, there, and this the ohmic dissipation is there. So it doesn't mean, it is not like this one to that energy is getting not getting there. That means it's getting destroyed. No, it's just redistributed. Yeah. So then, so the magnetoconvection, I'm not going to detail. So this is the theory of the sunspot. So as you ask, like different ways, so if you study this magnetoconvection, linear theory, non-linear theory, there are like a lot of theories. So suppose if you are heating this, and this is going, and you know the heat transfer is happening, but if you have a magnetic field structure, you see this area, they get like suppressed. So this is the flux tube. I'm going very qualitatively here because I'm not doing any mathematical calculation. But if you see the magnetic field, because of the tension, the magnetic field doesn't allow to flow come inside this. So if you are interested, you can go these two things, and they're like very informative if you want to study more about them. And so the sunspots, so there is, that's why this image I gave. So if you just zoom out, it's just the same thing you see, that these are the magnetic, the strong region. And this also gives this idea, the magnetic field in the sun probably comes as a flux tube. So whenever the magnetic flux are like more stronger or stronger, they just become intermittent. So they come like all together and create the flux tube like structure. So this is kind of the basic idea of this. Now the sunspot cycle is covered and the sunspot you see. So we eventually will go that how the sunspot is like forming. So the first part, if you see the bottom of the convection zone, I was mentioning they have the tachocline. Remember the tachocline where the radiation transfer to convection is happening, and the tachocline region, if you go to the differential rotation I showed, below tachocline region, sun is rotating as a solid body, no differential rotation. So this is the region where actually magnetic field get amplified. So that I will come later on. So then the flux tubes actually stays there. So you can imagine in that way. So there is like flux tube and the energy is getting generated there. And now you know that if you put something in the is a buoyancy again. So magnetic flux tube is in a plasma, in a gas. So inside the magnetic flux, they have a magnetic pressure. So if you calculate this magnetic pressure outside of the tube, it's like the inside pressure of the flux tube and the pressure exerted by this tube to the outside is the b square by 2 mu. So if you do the CGS, it's the b square by 8 pi. Then the outside pressure, so if you see the inside pressure of the flux tube, actually P out minus b square by 2 mu. So the inside pressure is always less. So if the pressure is less, you know, it will go buoyant. So that's why the buoyancy works. So that idea was formulated in 1955. And this is the so genuine idea and the very novel idea that for the all sunspot formation and everything, people do the magnetic buoyancy calculation. Then suppose you have this is your bottom of the convection zone and your flux tubes are standing there. But now because of the magnetic pressure and everything, this inside of the tube, it gets buoyant and it eventually rises. And the support for this is like if you see the magnetic, the sunspot photo, these are the huge black region. So they are originated from the foot, like from the below. So that's why it has been found that this is just going and they are creating a bipolar region. That's why sunspot always come as pair. This is the positive and this is the negative. So it is again the convention that how you are looking it, how you are looking this part. So if it is a positive, that means like the polarity measurement, you know, the polarization. So how it is coming towards you and coming. So that's why the sunspots are always bipolar. No. Toroidal magnetic field, I will go into detail. Toroidal magnetic field is like when the magnetic field, you know, in a toroidal, this is like the two shape. So from the observation, we can differentiate this magnetic field in two parts. One is toroidal and the poloidal. So toroidal part is like around this phi. So then now I come to the dynamo. So dynamo is a physical object or system that converts the kinetic energy. Now you see you have nuclear reaction, that is your radiation energy or nuclear energy that getting transported via radiation, and when the convection coming, convection actually transporting in the kinetic energy, motion of blobs, motion of gas and everything. What dynamo does, dynamo takes the fluid motion everywhere and it creates magnetic energy out of it. So that's why dynamo is a process which is creating converting your kinetic energy to the magnetic energy against your ohmic dissipation. So it's a hugely turbulent system. So you have the all scale of dissipation. So against this dissipation, so your energy dissipation is happening in a turbulent scale, but you need some generation mechanism. So that is called the dynamo. Now that's why I wrote here that what are the energy conversion happening? In fusion, mass is going and becoming radiation and thermal energy. Convection is making the kinetic energy, and the dynamo is kinetic to magnetic energy. So now I will eventually from the observation will build a model where you can explain this. So little bit of equation, otherwise you know we cannot say everything qualitatively. This is in Vaibhav has a talk where he will introduce your hydrodynamics and magnetohydrodynamics, and this is very important because this is takes care of the behavior of this magnetic field, fluid, everything, and these are called the MHD equation. So what MHD equation the first line showed, you remember in the solar structure what I did, if you're in a hydrodynamic equilibrium, then this part is 0, your advection part is 0, then you will get like minus gradient of P, your magnetic field is 0. So minus gradient of P is balancing the gravity. But now you see, now you have magnetic field. Now you have now velocity is moving, everything is moving. So you have to take care of the advection. You have the dissipation. You have the magnetic Lorentz force and magnetic pressure. So all things. Now the equation I showed is a very simplistic form of this parent equation. So these discover how the magnetic field actually relates with the velocity field. And the second one This is called the induction equation. So this is heart of the magnetic field. So this one is saying that how the magnetic field actually evolving with time. And you see, and it has incorporated the velocity v. So if you have a magnetic velocity v, it actually gets inducted with the some initial magnetic field, and that create the variation of the del B del T. Now what we do, like you have this MHD equation, so we always try to associate it with the scale system. So suppose you are working on this, all the laboratory plasma and everything in the laboratory, and you're doing something in astrophysical system. So how we quantify them? Because the equation is valid for everything. So we associated them with the magnetic Reynolds number. So if you scale down it, then the magnetic Reynolds number can be written from there, this part and this part. Then you see that this is defined by this. So for the laboratory, we know the magnetic Reynolds number is less than 1. So this induction part, like this part, doesn't play much role. This part, this del cross V cross B, because then the equation becomes like this, and then it's like mostly diffusive. You see, there is the diffusion equation. But if you see astrophysical system, this Rm is always greater than 1. That means it is mostly the induction. So suppose you have a magnetic field, suppose you have a velocity field and the initial magnetic field, it will keep on inducting. So as you remember, like the Maxwell equation, so suppose you have electric field changes, so that induce magnetic field. In this way, the velocity of the plasma, that is also moving, and that is inducting magnetic field. That's why this is the source term of creating magnetic field inside the sun. And this one is a diffusion, is a ohmic dissipation term. In general, we cannot do this distinct, but as a all or crudely you can mention this. But when you solve or make a realistic dynamo model, there is a dissipation, but the contribution of this term is like more than that one. That is the idea. But you will soon see that if your astrophysical system is Rm is greater than 1, what does that mean? I will come to this next slide. Sigma is the conductivity, resistivity, velocity of the plasma material. So it's not the electron or proton, it's like all of them. So this is the dynamo equation mostly. Now this is very interesting thing. Oh, yeah.
The magnetic Reynolds number, it actually different for sunspots and
No. The Reynolds number you can define all over the sun, but it is, I'm saying there is system dependent. Suppose for the sun, the Reynolds number will be same. But if you want to do in the laboratory, then since the system is very small and a small scale, the turbulence is not that strong, so dissipation might be less. So and in that system, you can quantify as Rm less than 1. Is velocity? Yeah.
like in case of
No, that is true, but the order of magnitude doesn't change much. So if you go to the solar interior, Reynolds number will be some. If you go to the atmosphere, that will be same. Different, of course, that is for sure. But we are talking about the astrophysical system where you have a lot of gaseous system. So there, the Rm is greater than 1. But if you go to the CME or coronal everywhere, that will change. That is. Sorry for this. I think I have to drink some water.
Reynolds number somewhere analogous to normal Reynolds number.
No, a little bit different. Yeah.
The ratio of the scalar it will come in
Yeah. But in the it's like the in presence of magnetic field, this whole system will be like represented by the magnetic Reynolds number. But in the hydro, you can go for the Reynolds number. It's also the inertial term by the diffusion. But here in this case, the energy generation, like the magnetic field generation, divided by diffusion. So the analogy is same, but since it's a magnetic system and magnetic field is being generated by this velocity induction, so that's why it takes care of the two measurements. Any more question? No.
What is the third term representing?
Which one? This one. This one.
Fourth.
This one. Oh, this is the diffusive. This is the viscosity. You know, if you have a velocity and you can it will have viscosity. So you know the viscosity is a representative of the dissipation. So that concept is a fluid viscosity. So then we come to the flux freezing theorem, and this is very important theorem in the astrophysical scenario. So since astrophysical scenario Reynolds number is greater than 1, so we have this equation. And diffusion for the time being we are neglecting. So now what does that physically mean? That means suppose you have a dipolar magnetic field, like magnetic field is going there, is north and south, and you have a plasma blob. So you are just magnetic field is like there, and you're passing the plasma blob in between. So if your Reynolds number less than 1, magnetic field won't do anything because it's not inducting anything. So it will just pass. But if the Reynolds number is greater than 1, that means this plasma blob decided how the magnetic field will behave. So this is the concept that when your Reynolds number is greater than 1, the plasma or the velocity field actually deciding the future of magnetic field, which is case for the solar interior. But if you go to the CME, their Reynolds number is less than 1, and their magnetic field is determining the behavior of plasma. So that is very important. And you can also assume it is very straightforward way. So this scenario is like, suppose you're going into a river and you just put something, that thing will go along the river, right? So this is just like this. So you have a river flowing, you throw some magnetic field there, it will follow the river flow. But if your Reynolds number is less than 1, it won't do. It will probably cross the river. So in the simple way, you can assume that. And that is very important for the dynamo generation, because in our astrophysical system is more greater than 1, and the differential rotation, that means the plasma flow has a shear, and that force the magnetic field to get sheared with it. So that is one of the important perspective from here. So then come to construct a dynamo model. So this is the solar magnetogram. So this is, you see, this is the surface of the sun. If you draw a line over here, you see these are the positive and whites are negative. So all of them dipolar, but it's coming in a group. If you see in the down, so there it is not very visible from there, but it will be opposite polarity. So then you can assume that the sun has a toroidal component, because in the below, if it is a toroidal component, then only it is rising up. So it's like observationally guided model we are constructing by seeing the solar magnetogram. And this has a poloidal field too. So this is also can be observed. So if you see this is a weak field, you see with the time, the weak fields are developed in the pole. So suppose it is sunspot maxima, weak fields are less. When sunspots are all decayed, this weak field will be more. So that has been found from the observation. And after seeing that, Parker suggested that idea that the cyclic nature is happening in the sun because this toroidal field, which is coming from the sunspot, they're actually getting decayed and getting the poloidal field. And again, poloidal field, which is coming inside the sun, creating the toroidal field, that means sunspot. So it's an oscillation. Sunspot decays and gets the poloidal field, and poloidal field again inducted gets the sunspot. So it goes on. That's why you see the cyclic nature all over the time. So that is kind of idea put forward in 1955. Then in last 70 years, like we have developed a lot in this regime. So we'll come to this one. So this is the fundamental idea put forward, and that's why actually we differentiate the total solar magnetic field in two parts. One is toroidal field, another is poloidal field. Oh, that I'll come. So toroidal to poloidal, you know, toroidal, this is going to sunspot. The sunspots are like strong regions, so they diffuse, and then they create the poloidal field. So I'll come to this scenario. Yeah, so this is the omega loop. White means it's going and one is going down. Black is going down, white is going up. Black is, if it, white is positive, then the black is negative. It's just convention how you're putting it.
Simple picture of toroidal field.
Mm-hmm.
And you said that due to the buoyancy,
it will rises.
It will rise up.
Uh-huh.
And that is
Sunspot, yes.
But if you look at it, you see there's some latitude difference between the positive? I mean, it's sort of tilted, right? So how does that tilt in the flux tube happen?
But that tilts, like when it rises through, is very good question. So when it rises through, it's like rotating. So this Coriolis force actually put this. So that is also that if sunspot doesn't have a tilt, it would not have decayed and create the poloidal field. So it's this photo I'm showing in the inside, but when it goes, it indeed creates the tilt. So that is true.
That sort of.
Yeah. So when you have the in the between, so it is going up, and you have Coriolis force, so it gets tilted. It is just like Earth when you have the from North Pole, the wind is coming to equator, it gets deviated. No, Coriolis force similar way it gets deviated. And then yes, so this is whether this idea which is put forward by Parker is true or not, that you can see by measuring polar field. So this first axis is the polar field in the North Pole and South Pole, and this is the sunspot number. So you see when the sunspots are stronger in the pole region, the fields are less because sunspots have not decayed. So sunspots are there and we have a weak polar field. But in the sunspot minima, when your sunspots are all decayed down and created the poloidal field, you see the polar fields are stronger. So the Parker's idea actually verified from the observation that the solar magnetic cycle is nothing but the oscillation between this sunspot field or toroidal field to the poloidal field. So then, and one thing I should say, this Babcock, they're like son and dad. They developed this thing and they did a lot of work. So they first detected this poloidal field. And they gave the first idea that dynamo can operate in this. But from 70s to 90, that idea, nobody looked into it. And then after 90, again, that idea came in. So that is very interesting thing. So then there is indeed an oscillation between toroidal field and the poloidal field. So then that's why when we are designing something, we assume that the magnetic field is like toroidal component and the toroidal component and the poloidal component. Now here comes to your question that how toroidal field has been created. Suppose you have the poloidal field like the North Pole, South Pole, and sun is rotating differentially. So in the equation you see there is a term del cross V cross B, the induction term. So when the sun is rotating, so this part is not rotating faster, but this part is rotating. So there is a shear going on. So this shear is actually creating the toroidal field. So it's a continuous supply of this field which is coming from there and it is creating the toroidal field. And then when this toroidal field rises up, the symmetry breaks. That's why the polarity changes next cycle in the southern. Suppose here S and N, in the next cycle it will be N and S. So the symmetry breaks. So this is called the omega effect. So since if sun doesn't rotate differentially, we would not have seen that. So probably sunspot might not have come if it is a phenomena from the toroidal field. So this is kind of idea of the how dynamo model actually creates from the toroidal field. So this is again one part. Now we have to understand how from the sunspot field, poloidal field generated. So there I want to give you some history. So when this part is given, so people thought, the sun is highly turbulent regime. So turbulence is going on and the turbulence also can create the magnetic field because the turbulence, there is a energy dissipation. If the injection is going on and there is a initial magnetic field, it can amplify that. The turbulence is very important in this regime. So then people thought that when the magnetic field is just rising, it gets distorted by this turbulence and that creates the helical convection. And that helical convection actually can convert this toroidal field to the poloidal field. And in this case, we do not need any sunspot because sunspot might be a byproduct. But when this field is rising from the bottom to the surface, while traveling through it, turbulence actually changing everything. So this is kind of idea was there for 20-30 years. Then around 90s, we find it out that that idea didn't work from the observation. So I'll come into this one. So I just first explain now, suppose you have a toroidal field from the differential rotation, how that toroidal field due to turbulence can be transported or converted to the poloidal field. So toroidal to poloidal, now the question is, now we'll go like which method is suitable for doing that. By this time you all understood that is a solar cycle is a oscillation between poloidal and toroidal. Toroidal field has been generated by the differential rotation. If sun doesn't have differential rotation, we forget about it. Sun has differential rotation, it's creating the toroidal field. Now our question is how to keep this oscillation. We need now a mechanism which will be converting energy from the toroidal to poloidal, right? So now, so this is called the mean field dynamo theory. So since the total velocity field in this case, what we do in the mean field theory is the solar convection zone is turbulent. So is a statistical ensemble average. So mean field theory. So we assume that all the small fluctuation, we can put it as like the mean flow and in a fluctuation on top of that. So these are the ensemble average. So all over the many measurement and this mean flow, then you have the P prime. And similarly, we can do the magnetic field as a mean magnetic field and the fluctuation. Now you put back this in the induction equation. Remember, this is the energy generation, the magnetic field generation term, and this is the diffusion term. So you put back here all this and you do some mathematics, and you see these are you get same equation recovered, but in terms of the mean magnetic field. Now same time, remember there is another term came. That term takes care of the small scale turbulence. All the turbulence and everything, whatever is happening, that term is taking care of that. So this is the term which takes care of the mean magnetic field. Hence, if you have a differential rotation, you have initial magnetic field, it creates the toroidal field from the mean velocity. This term, this is actually takes care of the poloidal field. And this then you understood that the poloidal field is coming because of the small scale fluctuations in the turbulence. And we, from the mathematical theory, we can actually wrap it up in a mean field coefficient, because all the turbulence now inside this term. And this term has many components. So this is not very straightforward, because now you have to calculate this from the many approximation that how the EMF looks like. You see, the EMF is V prime cross B prime. All the fluctuating part is there. So then we parameterize them using called alpha effect, diffusion effect. So many things are included in this. So eventually when there will be talk by HD and MHD, it will be covered that how the mean magnetic field and everything, this is generated from here. So from this slide, just take this message that toroidal field is generated from this induction part, but the poloidal field is coming from the from this small scale turbulence. So this is I can then the Parker qualitatively also make and understand a statement like how it works. So I'll briefly come to this. So you have toroidal field. So now the toroidal field starts to rise. So when it started to rise, it can be distorted by the convection, and that is create this helical convection. So if you can calculate this del cross E, you see there will be a term is 1/3 V prime cross del cross V prime. And if you remember, suppose you have a particle, a charged particle under electromagnetic field, electric field and the magnetic field. You see it do a cyclotron motion, and it's propagating along the magnetic field direction. So in the same way, suppose, although we are assuming the field strength, so if this particle comes under this, it does a helical motion when it's rising to the surface. And this all helical motion, since they are opposite, they cancel each other and create a large scale poloidal field. So that is the idea, that from the toroidal field, due to turbulence, they are actually creating this poloidal field. And this idea was given in 1955, and this model has issues because that time helioseismology was not there. Helioseismology didn't give the differential rotation. So, but somehow people knew that the differential rotation is there because of surface observation. And the differential rotation that they assume, that was completely different than the helioseismology finds. That's why that model that time was able to reproduce the butterfly diagram. But when 1990, the helioseismology came and it shows the differential rotation is completely different, then this model came into the problem. And also that was not only the reason, and also when you want to do this helical convection, you need such a field strength so that the velocity can distort them. Suppose you have a 10⁻⁻10 Gauss of field, like neutron star, then the velocity will not be able to twist it. This is a strong magnetic field. It has a magnetic tension. And although your Reynolds number is very high, but your equipartition energy, that is like so strong that velocity cannot take care of it. So that's why this model, around that time, we didn't have any idea how the field strength and everything, but around 90s, Okay, so before I go to this story, you see this idea was given. Then, so the now basic idea is you have the poloidal field, you have the differential rotation, and it's creating the toroidal field, and then the helical turbulence actually inducting and creating the poloidal field. That is the classical dynamo theory. Now, when this De Silva and Choudhury and some few other group did some flux emergence simulation. So what does that mean? So that means when I said, you know, you have a toroidal field and the sun, you're doing a simulation, the sunspots are forming because of the buoyancy. In the solar surface, you can see over time that how the sunspot tilt and everything looks like, because when it is coming up, because of the Coriolis force, it gets tilted. So as you ask, on the solar surface, you see bipolar sunspots are not like straight line; they have a tilt. So to explain that tilt, there are many simulations which they started with the flux emergence simulation. They started from the bottom and they put the convection, they put Coriolis force, and then they saw that to explain the observed surface distribution, you need a field strength which is 10 to the power 5 Gauss. And that field strength is so strong that the helical turbulence cannot induct this method. So this method then showed that the idea which was given in the classical dynamo, it actually will not work. So that was one. And also with the observed heliosismology differential rotation, the equator what the butterfly diagram I showed, the sunspots are happening at the top and it is going down. That was not explained. So that is kind of the two things which came into the picture, and then that leads to another dynamo model. So that leads to the Babcock who discovered the sunspots are decaying, you remember? That can create the poloidal field. So that comes like the Babcock-Layton dynamo model. So this is the now favorable dynamo model to explain many surface feature, solar magnetic cycle, your solar prediction, everything now we do based on this model. But this model also has some flaw. I will go through this, but this is the most favorable method in the current time. So any question in this, like why, you know, that a model has been built from the turbulence and everything, then suddenly we realize that with the other simulation and observation that this is not working. But this is the way the science goes, that you have a model you want to explain and you see that some of the model parameter are not well constant, and when more observation came, we tried to do more elaboration and more constant, and we see some of the things are not able to generate what people have been thinking of. Yes. Yeah. So you know that in this model, this part has this problem. Like you have toroidal field, then when it is going from the bottom of the convection zone, suppose you have this two layer, this is your R, this is your 0.7. Now you know flux are rising like this, right? So when it is rising, it gets like the helical convection like this here. Oh, I'm drawing very badly. So this is helical turbulence is happening. So to do that, you need like weak magnetic field, not very strong. Because if your magnetic field strength and flux tube strength is very strong, then the velocity field cannot induct. So, but when this model was constructed, we didn't know that what is the strength of the magnetic field in this region. But in 90s, there are like few simulation who did this flux tube simulation to create the sunspot. So when they did it, they find that in order to match with the observed sunspot distribution, we need around 10 to the power 5 Gauss of field in the bottom. And then we found that this magnetic field is strong enough, and the velocity field which is there, it will not be able to do this induction, the helical induction. So then it has been found that some other method then of course working, because you see sunspot cycle and everything. So then this model came into the picture, but also you see the basic idea remains same, but instead of helical turbulence, there is like some other method should be there to calculate the poloidal field. So these parts needs to be changed. Then yes, so then I put this, the world is like everything is like they are obvious, but people do not observe. So we already had the sunspot and it has a tilt, and some people already proposed this idea that when you have a tilt, that it can create the poloidal field. But we just completely neglect, or I do not know, sometime that time the classical theory was looking very promising, but that's why this idea was like overlooked. But then the Babcock-Leighton, their mechanism come into the picture, and from observation and everything, we find that this is indeed the mechanism which is doing this. The conversion from the toroidal to poloidal to toroidal to poloidal. Yes. So then, so how this Babcock-Leighton mechanism works, I think by this time you guys understood that there's a sunspot formation happening when this flux tube just rises. So this is the 3D view. Suppose we have a tachocline region, it rises. But you see, for that, what we need? We need differential rotation, very mandatory. We need magnetic buoyancy. We need Coriolis force and the turbulence mixing. So we need also decaying, because when the sunspot goes, you see, if you have observation of sunspot, they decay over time.
Outer layer
The tachocline region, so differential rotation also has a radial variation.
I thought you
No. This is the inside. Surface you need on the diffusion. So now you see, this is like rising up and creating the sunspot. So this is the importance of the tilt. You have positive, negative, and this negative, positive. When with the time they go towards equator, with the time, the equatorial migration, then this negative, positive actually cancel out. But there is a meridional flow, which is discovered by heliosismology, like the large scale flow, like our ocean in Earth. This actually diffuse this field to the pole and create the poloidal field. But it sounds very simple, the way I'm telling, but it is not that straightforward. Wait a second. To do this, the flux freezing theorem should be valid. Flux freezing theorem, otherwise magnetic field won't follow the velocity field. So that is there. There is a reconnection of the magnetic field so that it gets cancelled out. That is there, and also it is 3D. It is latitudinal dependency. So in the sunspot, so if you now measure all the sunspot position and you see their area and how much they are like separated, then you calculate out of the flux, like how much flux is actually remaining after cancelling out. You see this is actually happening. So that is kind of observational fact. So that's why I put the observation support set. 2011, 2010, there is a many paper. So where, yeah. Oh, because with the time, the sunspot, they had to come together, right? So with the time, sunspot appear here in the beginning of the cycle, and with the time it goes towards equator. So that's why if they do not come towards equator, then there is no chance. Only it will diffuse. No, but that is with the time. The toroidal field is also changing, and there is a meridional flow in the below. So suppose the toroidal field which is getting buoyant, it is in the convection zone, is like higher latitude. With the progress of the cycle, it goes. No. So suppose with the time, all the toroidal fields are there, right? So at beginning of the cycle, suppose this part is like going erupted, but when the cycle progress, some of them are erupting here, and because there is a meridional flow, this is at the surface, and there is a inside the one cell flow. So this is actually taking it. So there is this is called conveyor belt, and that determines the sunspot's cycle period. So the meridional circulation plays a very role. So I'm just telling the poloidal and toroidal component how they are generated. Now when we'll show this magnetic field of the dynamo model, you'll see the meridional circulation also plays very important role. So that's why it is happening. And when this model was prepared, so many people thought we do not know whether there is a flow exists in the bottom of the convection zone. So then recently people found there is indeed a flow which is taking this. So then that's why it's one of the criticism from the model that there might not be any meridional flow, but heliosismology is finding it now.
is it sort of like this, or is the whole sun?
No. Surface, so if you're seeing this, the pole is 20, so both of them are rotating like this. But some of the part in the pole that might be slowing down and the equator is rotating faster. So in the background, you can assume the 24 days rotating, no, sorry, 30 days, pole and equator rotating in the same speed, but equatorial material might be rotating faster. Huh.
I don't know why I imagine it being like this.
No. That is no. That will be like too much. Then sun will not be stable.
Study very basic.
Huh.
By a simple ring, right? A simple current flow, and then you'll have a polarization. So why doesn't that current?
No, but here it is like the plasma flow, no? Here it is not like some current changing. Here is the velocity. It is just like this velocity is like getting seared. It is just like a, how do I say, a rubber you take, that will be a good example. Then if you twisted it, the rubber, then it is doing. It is not kind of any induction happening here. So in that way, this velocity sear is inducting this toroidal field. Okay. So then this is, now you know the toroidal to poloidal and poloidal to toroidal, right? So now we can, now this dynamo is, see this part is now changed. So there is a differential rotation creating the toroidal field, then from the toroidal field is the Babcock-Layton, and the surface thing is doing it. So now if we model this, so this is the flux transport dynamo. So what is happening here? So this is your tachocline region. This is a meridional cut now. So in this region, you see this, the toroidal field is generated, and with the time, maybe in the beginning of the cycle, some sunspot is just getting erupted here, and with the time, it gets erupted here. That's why you get the equatorial migration. And when it is going there, with the time, it also propagates there, because it's a buoyant rise, and then they are cancelling on the surface. And when the diffuse magnetic field, which remains there, which cannot get cancelled out, that is taken by the meridional flow. Is it too much information? But this is the kind of basic dynamo model, so where you can explain all the solar magnetic region. So after this talk, you guys can talk to me like all the details and everything. But this is the very basics of this stuff. And so you know that this procedure by the model when we develop, these are like all 2D model. But you see the sunspots are like 3D structure. So we didn't have the option to incorporate all the sunspot data and everything. So the model itself gets like evolved with the 2D model. So in the 2D model, this whole procedure we parameterize. As if like we did like the whole turbulence thing, we parameterize in a alpha helical motion. In this case also, we do an alpha mechanism, which is called the Babcock-Layton mechanism. But recently, we have also developed a 3D model where you can actually put the sunspot, and you'll see they are decaying and they are creating the poloidal field. So that is the way. So we try to mimic the sunspot surface. The way it is happening there, we also want to construct a model in 3D. So that is like being started, developed from 2015, 2016. So now this model is getting and getting like much more developed, and they are going to explain many of the features. But this model I'm saying is the 2D model. That's why everything is parameterized. But in 3D model, you can actually do all the surface observation in your model. But that is, yeah. Sorry. Oh, I can tell you. So, you know, there is a radial sphere. So there is the poloidal field is coming and creating the toroidal field. But with the toroidal field getting magnetically buoyant, I saw the pressure is inside is less. So it starts erupts. But you remember the flux phasing theorem I said, the meridional flow actually decide how the magnetic field will behave. So this velocity is such that with the time, it takes this field towards equator. So when the field is there and something is getting buoyant, it rises at 45, 50. But with time, this goes in. That's why it's called the solar cycle clock. And it decides the solar cycle period. And eventually we will see that this is like what I was saying is a 2D model. That's why we do everything in a parameterization. Because when the sunspot erupts, it is not a 1D, like not a 2D thing. It's like 3D structure. So the diffusion and everything is itself 3D. And even here, I'm saying in a meridional flow, but it is a huge spherical region. So you cannot do only one thing. So you have to do in a theta and phi both. So that's why in many stars we even see active longitude. That it is not only latitude, the longitude is also different. But for the solar case, that thing is less. The axis symmetry, you can say, is like valid for the sun. So then with the time when it erupts, so first time it erupts here, with the time it is going down, something is erupts here, it is also going down, so they cancel out. And then the remaining thing, which is the surface meridional flow, takes to the pole. So then the cycle completes. So that is the basic idea of the dynamo model. So you decompose your model from your observation, your toroidal field, poloidal field. Then you see how it's just oscillating between each other, because you have observational constant that poloidal field and toroidal field indeed relate to each other and oscillatory. So then you develop this model. But as I was saying, this is 2D, but it seems like it's very simple or straightforward. But when you're putting, there are a lot of things going on. But eventually we'll come into detail. But my idea is to give you that how this dynamo mechanism actually creates the sunspot and the solar cycle and everything. I think. So that's what I showed the heliosysmology finding, remember? So they find it now. It was debatable that whether it is coming to the here or it comes back here, because if some of the material is going there, it has to come back, otherwise mass won't be conserved. But it found that some of the things, the people are like a little bit skeptical whether that is coming below up to the convection zone. So then 2020 paper, science paper, they showed that it indeed has like the single cell, like it goes up. So you see that's why it says like the order, I mean, it's like this much chaos. So there is a lot of turbulence, lot of convection, many things are happening, but still we find a systematic flow. So that is the beauty of this meridional flow structure. You see there is a lot of turbulence happening, but still we see beautiful things. So this period is case 11 years. But meridional flow, it depends on the speed. So in the surface, it is 15 to 20 meter per second, but in the below, it is like 2 to 4 meter per second. Yeah. So this is like if you do like the convection simulation, then you see there is a lot of energy transport. So what is happening? So that is another, I have to give you another lecture. Yeah. So, so when the convection, so suppose when the convection cells are rising, so I can briefly tell you like very qualitatively. So when your convection cells are rising from the below to up, so the Coriolis force is like deflecting the material towards the equator. But in the solar case, we also know the pole temperature and the equator temperature is different. So that there is a poleward flow. So there is so there should be a balance to create a steady state flow. So something is transporting towards equator, something is transporting towards pole. So then there is a balancing, and that balance is done by the meridional flow. So for that, you have to do like global 3D convection simulation. So initially you put the flow, you put your, again, composition, opacity, how this energy is coming, all things. Then you do the convection in presence of magnetic field and the rotation. Then you see where the energy transport is happening. Then you'll see this large scale structure actually has been developed from there. But till now, we are far away from the solar parameter space, because if the Reynolds number is so high, we cannot go that high. But qualitatively doing like, these are called large eddy simulation. So you know that these are the scales of like huge scale, like sun is much larger. So in computer, if we want to resolve like very micro physics and the large scale physics, so the computer we cannot do. So that's why we average out the small scale fluctuation, and we want to see which scale is important to explain this large scale flow. So these are the large eddy simulation. So many people are doing it. And then again, you have to compare the heliosysmology, whether your simulation is giving a correct result or not. Meridional flow does it, yeah. But I do not know whether it's still, but it is responsible for that. So this is, yes. So this is very important. The speed of the meridional flow actually determines the solar cycle, and this is quite consistent with the observation. The heliosysmology also find this is like a 2 to 3 or 4 meter per second, and which can give the 11-year cycle period. So now I want to show you like little bit glimpse of the 3D model. So that is all the turbulent transport. So at the end of the day, you're talking with how energy is getting distributed all over the cell. So how your convection zone, so if it is like instead of 0.7, if it becomes 0.5, then it will take more time to get the energy transfer. And so many things, I cannot say like only one thing is doing this. So there are like a lot of transport, lot of things is happening. So you have to do it self-consistently because all of them are related to each other. So I cannot say like this determines this. Multivariant, and it's like totally depend on how the angular momentum, energy, everything is getting transported in the solar parameter region. But that is in MHD talk, if I give out, MHD, it will be covered. So Vaibhav will be saying, so some of the glance you will get from there. So this is one of, any question? And this is the one of the model from the 3D dynamo model. As I was saying, you see sunspots are coming from the below. So now we put the sunspot. So now with the time, this leading polarity sunspot, they are coming towards the equator, and leading polarity here, you see opposite polarity, they will cancel out and they will go to the top. So that is when we put this from the toroidal field, and their frequency and the distribution, we get it from the observation. When we put it, we see it indeed create the poloidal field. So this is the, so you see with the time, it's a little bit fast. You see they will be like getting decayed and the poloidal field will be created there. The sunspot is getting decreased and poloidal field is getting there. Again, another cycle started. So this kind of 3D model, here you can do all the methodology, what we are saying, you can get it from there. And then this is the result from simulation. So this is the, now you get the 3D, but to match it with the observation, we did a azimuthal average because it has 5 component too, but we have latitude and latitude. So we did a azimuthal average. Then we plot time latitude diagram. So these are the each cycle, but this time you forget it because in simulation we can simulate 3-4 cycle over any time scale. So assume it is like 1 cycle, 2, 3. Then you compare with the observation. You see this methodology is quite nicely generating the butterfly diagram. So now, is that all? No, because this model. Yeah. So there are a lot of studies, yes. So these are time series, you're right. And we find that some of the parameter from the previous cycle actually correlate with the other. That is found. So, and that actually creates, here you see this, I am producing all the cycle are like similar. But if you see the solar cycle, one is weak, one is stronger. And as I explained before, the meridional circulation is relating one cycle to another. So there should be a correlation, and people found it. So you are right. Like cycle 23, if you see how the meridional flow speed, that relates to the amplitude of the cycle. So various quantity, of course, we can do. That is good point.
Please pretty much does it also agree with the sunspot maximum?
Yes. So in the 2D model, we didn't have the physical sunspot number because we are parameterizing everything. But in this case, you see the sunspot numbers are there. So we it's perfectly matches with this. But we have drawback. So one of the things is you see the strong poloidal field. But in the observation, it is not that strong. So why it is happening still, like we need something, maybe diffusion we are overestimating, or maybe meridional flow sometimes takes this material with it to the inside. So we do not know this part. But there are like some indication that if we include some of the thing called turbulent pumping. So the fields are trying to go and diffuse everywhere. But if you can put the strong turbulent pumping, it can diminish and it can take down. So that can give a polar field measurement perfect. But that is still an active field of research now. So how the sunspot cycle and everything is changing and what are the parameters we needed. So I just wanted to give you a brief thing that we have now, even in India, we are doing pretty well in this, that we have 3D dynamo model, we are doing forecasting that what will be our solar cycle look like and everything. So this is kind of like glimpse of many things what we are doing. So now you ask me like, oh, well, we have simulated the solar cycle, butterfly diagram is going well. So what is the use of it? So the thing is now, if we understand all the procedure, all the meridional circulation, then by constraining them, we can predict the next cycle. So if we understand the physical procedure, so in that will help us to plan our mission and everything, the space weather, everything well. So that is one of the aspect. Another thing, we can extrapolate this. At the end of the day, coronal magnetic field is coming from the photospheric magnetic field. So if we can nicely understand how the photosphere and everything is going on, then we can extrapolate to get the coronal magnetic field. So that is also another branch of, like, now many people are interested, because coronal magnetic field not only affecting our space weather, like on our Earth, it is also in the exoplanetary system. It is very important for the life in another planet. So, and since other star and planet system, we cannot detect them the way we can detect in our sun, because we have overwhelmed amount of data. So we can do whatever we want in that way, like microphysics, even that like whether it's a proton, hydrogen, whatever, like all the composition wise we can analyze them. So suppose you do this, then using this model, we can also predict the coronal magnetic field. So that is, I do not do that coronal magnetic field part. Just for your understanding, I just plotted this. So suppose you have a surface magnetogram, then using MHD model. So there are many models that how you will be extrapolating your magnetic field from the photosphere to the corona. And for this particular workshop, it is very important because you will be using a lot of data to detect our coronal magnetic field. And this is very important because whenever you do star-planet interaction, sun or earth interaction, this magnetic field plays a huge role in deciding how the planetary magnetosphere will look like, how the energy will be getting mediated because of this magnetic field. So everything. So this is one of the glimpse I give from this paper. So you see, this is the minimum. So solar minima, you see the solar minima sunspots are not much there. So that time you have, like, how do I say, dipolar magnetic field structure. It is a little bit complicated here, but you see roughly is a dipolar. Solar maximum, you see it becomes quadrupolar. So you have a different magnetic structure that will lead to different space weather event. So that's why understanding your solar cycle and how the sunspot and everything creating is very important for the coronal magnetic field. And you guys will be analyzing some of the data soon. So this is one aspect. Another aspect is this. Learning this MHD and everything, you can simulate the sunspot. So this is, I'm showing the simulated sunspot from the all fundamental physics. And this is observation. Can you differentiate both of them? The detail of detailing is there, and the microphysics, radiative transfer, penumbra, everything is like so well reproduced. So now, if you want to do a global corona, then you can do from the solar cycle and all the sunspot like previous simulation. Suppose you want to understand only a single CME simulation. Like suppose today a CME is directed towards Earth. You want to understand that CME. You can do a local sunspot simulation. So then this sunspots is like, you see the amount of detail we now can do is amazing. Then from there, we can even do like the extrapolation. Then we see whether this active region has the capability to do the flare or CME, even we can predict that. So this is the, I think, next generation ball game. So, and we are doing well. And with the Aditya, I think you guys will also help us in doing this. And if you get the coronal magnetic field measured, then that will help us to constrain our model. Because photosphere we can simulate from our model, but then this extrapolation method, how the corona is happening, that is also like very, very important part, and we do not understand that physics well. So if we can measure this magnetic field, and then with your lot of microphysics, we can actually produce the coronal magnetic field, and we'll see that how it is going to affect the space weather. So with that, I stop here, and if you have any question, I'll take it. This one. Oh, this is we have each day observation, even hour. So these are like they are very nice. So we can have like all detailing, whatever you want. For the star, when we go for the solar-like star, there we are facing problem. But for the sun, we have enough data. But we are like, we need people are building more physics-based model. Because in the computer, we cannot simulate all of these things together. You see, these are the large-scale feature only we are producing. There is a granular structure, and there is like convection going on. So all things we are not putting in. Here only I put the sunspot and the meridional structure or the mean flow, but how the convection is disturbing them, all of this stuff. So these will be doing in next 5-6 years. And I think in the solar physics future is bright. You guys, if you can come, we have like in-house expert, we have Aditya going on, and whatever you want to do, you will find person. If you want to do the solar interior, if you want to do heliosysmology, if you want to do the coronal magnetic field, if you want to do in space weather, and if you want to do exoplanet, I am also there. So everything. So I think, so if you are learning this Aditya thing, that will be very fruitful for your future thing. Oh,
It's better if you ask the question using mic. So
sunspots, if you see, they're like always in the group, but if you just separate out, they are in the bipolar structure. But what is very interesting thing, they do not always follow the Hale structure. So if it's a positive negative in the northern hemisphere and in the same time negative positive in the southern hemisphere, there are like few of them which are not following that rule. They are called anti-Hale. So this is the I do not know whether we understand it well, that why some of the sunspot doesn't follow Hale rule, but they have a huge effect in the poloidal field. So
and that magnetic field that look created that extend out to coronal region,
right.
and some that have open magnetic field called coronal hole. That is the what is the mechanism behind it that coronal hole produces?
Coronal hole, I think Vaibhav is the person to answer. They will cover that. Yeah, of course, they are like very interesting thing, the open source place, and they are like very important for the space weather.
yeah, so I mean they are open locally. It's not like that a magic system. They will close it eventually. I mean,
But a very large distance.
yeah. So that some of that can be reproduced from these magnetic extrapolation that he has shown. So if you go to that slide there, you can see the open magnetic field.
Yeah.
The
Yeah.
solar minima.
Hole in the
Yeah.
hole.
You see, there are many.
Yeah. Basically, these are how they exactly form, what causes polarity to concentrate there. That actually comes again from the dynamo mechanism
thing.
because of these deep conductor mechanism.
Right.
And opposite polarity migrate towards
Yes.
the hole during them. But the other ways also you can form coronal hole, the interaction between the active region.
Yes.
And then there would be CME that will open up the magnetic field. And then also you will see on this one.
Yeah, that is very interesting part.
Questions?
So you told that we detect helioseismic like signals through Doppler spectra, right? So also there are like convective flows on the surface. So how does the magnitude of both of these compare?
Oh, that is very important. That is heliosysmology. People are getting trouble with this lot. So that is they do like from the simulation or perspective, they get the convective blue shifted already measured, then they correct it in the heliosysmology data.
Okay.
So that is there. They are perfectly right.
Okay.
So we take care of that one.
Okay. Thank you.
Questions?
A very famous correlation known as Waldemar effect of
Uh-huh.
sunspot time series.
Right.
So does dynamo model support or has some
Yeah,
evidence
yeah.
for that?
So there is like a lot of study with this model I showed. And the Waldemar effect already can be explained using the Babcock-Clayton mechanism. But the thing is, that wherever I showed here all the model, they are only creating a time series which is symmetric, like which is same amplitude. So we need to understand what actually causing this solar cycle irregular. Something is weak, something is stronger. Amplitude. So, but you see in the simulation, what I showed all are same amplitude. But oh yeah. So yes. So if you do irregular, yes. But then you have to introduce more. I didn't cover them. So that is what happened when you're taking the sunspot on the surface. It has a stochasticness inside it. So and that depends on the cycle to cycle. If you have a stronger many sunspot, that will have the different stochasticity. So then you have to take care of that. And also meridional flow varies with the time. It is not always like 3 meters per second. And if the meridional flow varies, then there is an interplay between that how fast sunspot will move or how fast it will decay. So if the meridional flow is faster, the sunspot will not get enough time to decay. Then it will create the stronger cycle. So then you can explain the Waldmeier effect.
Some dynamo models, I think I read a paper by Debendu Nandi. They have extrapolated on decadal time scales, the sunspot time series. So that kind of contradicts. I mean, you don't need the local information about the sunspot, right, to predict larger time scales.
So when you are seeing that, you need at least a year smoothing or something. Decadal, yearly will be okay. But the decadal, if you take, then you might lose many information, because the poloidal field and the toroidal field, the polar field, and that is within a cycle is related to the next cycle. So if you just completely neglecting the decadal, then you won't be able to predict properly.
Okay, wait. So we have been talking about the toroidal and poroidal fields. So I wanted to know how the magnetic flux conservation goes, because we are saying that the poloidal fields are very weak compared to the toroidal fields.
Yes.
If the field strength changes, the magnetic flux should also change, but magnetic flux should be conserved.
No, that is very good question. Magnetic flux should be conserved, but since when your sunspot is going, so there is a decay of fluxes. So and there is a diffusion scale is also there. So it is not at all like fully conserved system. It has a dissipation inbuilt. So that's why like some of the field which are getting like decay down, if you go again going down in the bottom of the convection zone, there is an induction. So again the field is creating.
So the total field
remains
flux is conserved.
But as a longer, if you go for the evolution time scale, then might not be.
So when the sun was young, I guess it will have it must have a strong magnetic field.
Yes.
Now it is
getting old. But if you are only taking in a like 10 years, 11 years, then it is okay. Because
they usually don't have positive and negative charges. So the magnetic field is explained using magnetic flux conservation.
But in this case, magnetic flux conservation is like getting broken because there is a reconnection and symmetry breaking. But as a total, it remains conserved. But on the evolution timescale, it is not, because when the solar wind, CME, it is also taking a lot of magnetic flux with it.
The
outflows. So that's why, like, if you consider angular momentum transport, like magnetic field transport with angular momentum, you'll see a lot of magnetic fields are going off. And that's a good question.
No. Yes. How does viscosity plays a role in like the in sunspot?
Viscosity it plays very good role. One of the things is viscosity, we do not know actually exact measurement inside the sun. So if you change this viscosity profile, your cycle profile weakly dependent on this. As far as I remember, it is eta to the power minus 0.25. But it is not very strongly dependent on this, but it does depend. At the end of the day, viscosity is diffusing, right? So if you have a stronger viscosity, stronger diffusivity, your sunspot field will be decaying so fast. It will not get enough time to create the field. So that of course depends. But in the sun, from microscopic point of view, we do not have exact estimation of this. So that's why still we have to rely on the mixing length theory argument, that how the diffusion and the viscosity coefficient are. But that is still, I would say, helioseismology also couldn't give us a good estimate.
With the simulations, we can't.
With the simulation, we can get, but unless you have an observational estimate, simulation you can do whatever. Theoretically, we have, but observation, direct observation, we don't have.
I'll add one more question. What is the reason behind the differential rotation of that sun?
The difference, as I was saying that, so these are like all the convex, like, you know, the energy transport. So the sun at the end of the day wants to stay in equilibrium position. So if some places the convection is rigorous, then other places it has to need it. But I'm saying it's very crudely. But if you want to, that's why there's a angular momentum transport happening inside the sun, and it has been done using differential rotation and the meridional circulation. So if you do the convection simulation, and you will see the differential rotation has been created for fulfilling the angular momentum conservation.
Okay, that's why it is like faster in the equator.
Equator and the pole. But again, I'm saying it's very roughly. So if you have to do, then I have to give you a 1 hour lecture on this, that how it goes. But it's very interesting, because other Sun, you see the differential rotation, some slowly rotating star, we see anti-solar differential
Yeah,
rotation.
that's what I was saying. It is peculiar for the sun-like thing. I mean,
Huh.
sun-like stars, but in some other stars, poles might be rotating faster.
Again, it depends on your energy rate, how it is getting transported.
Mm.
Because you remember, you have to do like the stability. So
Mm.
sun and star, they always want to be stable. So then to fulfill that criteria,
Yeah.
there will be like some kind of rotation and this. But it case dependent. You have
Yeah,
to study
exactly.
based on all the radius, convection zone, density, everything.
And, you know,
But it's not at all straightforward. I have to give you like 1 hour lecture on this. But I hope you guys get like the at least fundamental essence, you know, that how it gets and everything.
When you say differential rotation, right? So do you mean like the surface velocity, or like what velocity exactly?
Differential rotation, you know that if you see, like I'm now talking in the mathematical version. So if you take the omega, that is a function of r and theta.
yes.
So if you go like radial direction, then maybe tachocline region is rotating a little bit slower than if you go like maybe r plus 10 kilometer away. This is one type. And if you see the latitudinal, that means the theta dependency. So theta equal to 0, for example, equator is rotating faster. But if you go to pole, it is rotating slower. But it's so in this way.
Okay, like that. Okay. So I thought maybe
No, it is
has
not
to do
like
with the
you
plan.
have this, one is going this, one is going this. No, then it will tear apart.
Yeah.
No, not that way. Like both of them is going, but some of them are going faster because it's a blob of plasma.
Right.
So it is like some of them are going off, but at the end of the day, everything remains constant.
Yeah.
So coming to differential rotation again, this differential rotation is very dynamic, unlike
Yes.
solid body. So we in general say that it carries a 24-day period far from equator and 30-day period from equator. So is there any variation in this differential rotation that is far from our measurement?
There might be I think there is a professor called H.M. Antia in TIFR. So
Yes,
they
yes,
have,
sir. Yes, I know.
so he has like few paper probably, but the variation is not significant. That can change the dynamo. But you know, it is not. They have error bar, and they will be of course change.
I think from Kodaikanal data observation,
Yeah.
they have measured differential rotation as a solar cycle. I think solar cycle. I think the variation is not much. At least at the potential.
Yes.
Sir, you just mentioned about there may be some other nearest star, the sun. They might have an inverse in, like the equatorial poles.
Which has not been observed yet.
My question
theoretically
was around
predicted.
same. Is there a study going on so that we can understand our nearest star better comparatively to other stars?
Yeah. Proxima Centauri, they has 2 habitable planets. So people are already started studying it. And Proxima Centauri is like much more active than our sun.
Okay.
So there are much study, but Proxima Centauri dynamo is not well understood, that how it is creating the magnetic field and stuff. But Proxima is like not having anti-solar differential rotation. It's very fast rotator, so it is mostly will have this, but still the differential rotation also is not very well mapped. Only the sun has everything. But you are right that people have already started looking in the Proxima Centauri. There are 2 habitable planets, everything.
Okay, so this is like estimated but not proved or observed yet.
No, not observed directly, but you know that from the other composition spectroscopic analysis, you can get the radius measurement and everything. From there, you can at least simulate them.
The problem with the stellar observation is that the stars look like a point object.
Yes.
Sun is very well extended, so you can study the variation with latitude. There, it is very difficult. You need to do some sort of inverse modeling.
And the error bar is also
strong. Yeah. So
we are trying to do this like the solar dynamo. You know, we are trying to do for the star, but we do not have any velocity, anything observed there.
But already for our sun, we have a lot of data.
Yes.
Get a lot of error plus
Yeah.
data out of
it. Yeah.
So like comparing it with other stars,
nothing.
Yeah, I mean, sun is very well observed because the nearest star.
Nearest
so that
star.
is.
And nowadays astroseismology is taking over, so we'll get a lot of differential rotation, meridional circulation. They will be coming in next 5 years, I think. The Pluto is coming. There is a Pluto is like another. It's not the code, by the way. It's Pluto is another mission. So we can see.
Okay.
Yeah.
Because of this differential rotation, magnetic field get twisted, stretched, then form a loop and comes out to the photosphere. So is this a critical limit or critical value
Yes.
because that magnetic buoyance pressure that will help to comes
Yes. So you see that equation I showed, like the P out equal to P in by B square by 8 pi. If the B square by 8 pi is not significant enough, that the inside is like strong, or even it is not strong enough to create the flux tube structure. So there is a critical value I remember is 10⁴ Gauss.
Okay.
And it has been found from the observed sunspot that we found that is 10⁴. And when it crosses more than 10⁴, then only it rises.
Sometimes we observe small magnetic flux.
That is, yeah. But those are like, those are maybe from the granular, I do not say, but the small ones, small structure, weak sunspot you can see there.
So small magnetic flux concentration at the intergranular lanes can also happen in situ because of the convection pattern. You have a convection, you have magnetic field, let's say uniform, and then there is a convection pattern. It will try to aggregate the magnetic fields at the boundaries. So that can be generated locally. You do not need like this type of global dynamo to generate those. But what he's talking about is the sunspot light.
So you remember when I showed that the sunspots are strong and they should be connected to the bottom. Otherwise, it will not create that big region.
And also, is there any magnetic field due to the plasma inside the core? Like
magnetic field inside the core.
If core is conductive.
No, that is we do not know yet.
I think in some of the simulation models, they assume that to be conductive boundary condition. So if it is purely conductor, you do not.
Then you cannot have.
Then you cannot have.
So that's why the massive star have this problem, right? The convection zone is the inside, so dynamo is there, but it cannot come out now. So that is one of the big issue. Yes, M dwarfs. Oh, so this solar-like dynamo might work, might not work. So you have to apply it and see. But since they do not have tachocline, so this Babcock-Clayton type dynamo might not work. So I showed the alpha omega, the helical turbulence, and since there's a small star, so the alpha omega dynamo might work. But this is, as you asked, so for the M dwarf, the convective zone, people are saying the alpha square omega dynamo happens. So alpha square omega is like, I said, like omega effect. It's creating toroidal field. Then alpha effect is creating toroidal to poloidal. But if you solve this dynamo equation, there is another term where toroidal field can be generated from the poloidal field via alpha effect. So there is a two effect. That's why alpha square omega. So many people are arguing that for the M dwarf, like low mass star, the alpha square omega dynamo is happening. But since we do not again cross verify, because we have very Zeeman Doppler imaging, like very tiny amount of data, that is also ongoing. So that's what I'm saying, that we need you guys to do this, like a lot of things to do.
Sunspot cycles, right? And in sunspot, the three-dimensional diagram you have mentioned about sunspot's cancellation over the image. So is it to add any kind of additional information, right? Like studying sunspot cancellation and the intensity of magnetic field over the core or something? So can we expect any kind of studies regarding that?
No, like there, no, I didn't understand. So we already doing this in 3D, but what are you asking? Like, is there?
To add any kind of additional information.
But this is additional information to the corona, or it like already I think these things are included, when there is cancellation happening, there is like open field or
associated with a white spot, we have a dot and the over the same magnetic field, and there is cancelling out the opposite polarity.
Oh no, that I'm not sure, because it comes as systematic way. So we have never seen that something is like overlapping with other thing. Then your very fundamental rule will not be valid, no? That the del dot be 0, because magnetic field always come, monopole doesn't exist. So that thing will not be there.
Further questions?
It's 10:01. I
think. Yes, seems everyone is hungry.
So I will be there. So if you have further questions, so tomorrow I'll be leaving. So today.
But tomorrow you are here before lunch.
Before lunch.
Before lunch, and today also he will be here during dinner. Also you can catch him. So because you guys have dinner at the same
Yes,
place.
and if you have any question further, so I give my email, you can write me. So this is my surname, iitk.ac.in. So you can write me that you attended or you have any questions, okay? Is it okay, visible?
Or if you have any inquiry about the
Inquiry.
positions available in his group, then also you can contact us.
Yes.
Okay, then, if we do not have any other questions, then let us thank Gopal again for coming here. And yeah, so now we have lunch and we reconvene at 2, right?
2, okay. दोनों वो 2 घंटे का लेक्चर है ना तो गला सूख रहा है ये भी खत्म हो गया